My name is Andre Neto-Bradley, and I'm a part of the team working on the EnergyFlex project, which brings together researchers at the University of Cambridge, University of Leeds, Daphne, and the Alan Turing Institute. This project has been developing novel simulation tools to help identify opportunities for flexibility and decarbonisation of the UK's housing stock. About 10% of carbon emissions in the UK every year are linked to the energy we use just to heat our homes. The UK government has recently announced a new heat and building strategy for achieving its net zero emissions targets, which aims to slash emissions by promoting less carbon-intensive heating technologies, as well as improving energy efficiency of homes to reduce consumption. Residential energy use is closely tied to the energy efficiency and thermal performance of the physical buildings that we live in. Designing effective solutions to improve efficiency and reduce consumption requires taking account of the building's characteristics as well as the socioeconomic context of the households living in them, in order to determine how affordable a solution would be, as well as which would actually offer the most cost-effective emissions reductions. One of the challenges to this is that while there may be some national smart meter datasets available and regional and district energy consumption statistics, there is limited data on the variations in household energy consumption and energy efficiency within a local area. For example, households living in flats will have very different considerations to those living in detached homes, such as the detached home may have the option to put in loft insulation, whereas the flat obviously does not. But official data on such differences is limited. Furthermore, the data that is available often does not link energy consumption to the socioeconomic context of the household. EnergyFlex addresses this challenge by using a microsimulation-based approach. Using publicly available data, we create a representative synthetic population for a local area. We then use energy models to estimate likely energy consumption and building energy performance characteristics for each synthetic household. Microsimulation approaches are not new, but they have been used more often in modeling transport and diseases, with limited applications into research on energy use. By combining modeling and calibration approaches previously used in building simulation with the synthetic population, we have been able to produce a representative sample of households with building energy performance characteristics and socioeconomic context for each of those synthetic households. This means EnergyFlex can be used to model differences in energy efficiency of homes across any part of the country, identifying areas and property types most in need of energy efficiency home improvements within any given area. What's more, the representative synthetic population can be used to simulate the rollout of different policies and solutions. This includes considering the emissions reductions possible through different retrofits, as well as the affordability of these to the households that they might benefit. EnergyFlex can also provide insight into possible flexibility in demand, which could become important with increasing need for electrical vehicle charging and storage in future. The tools being developed by the EnergyFlex project could enable local government to better tailor and target energy efficiency solutions for homes within their authority, matching households and improvements that are both effective and affordable to them. This could also support partnerships with the construction industry to roll out retrofits for specific property types within an area. And EnergyFlex could also facilitate planning scenarios for vehicle charging and energy storage in future. Thank you very much for listening, and do get in touch if you want to find out more.